Hi everyone, I'm Daqi Lin from University of Utah. Today I'm going to present hardware adaptive high-order interpolation for real-time graphics. This work is a collaboration with Larry Seiler from Facebook Reality Labs and Yuksel from University of Utah. In this work, we propose a new formulation of high-order interpolation, which allows us to use the existing texture filter unit on the GPU with minor modification to support high-order interpolation. As a result, we can do high-order interpolation with performance close to linear interpolation. This benefits a wide range of applications. Interpolation is widely used in computer graphics to get continuous appearance from discrete data. Examples include texture filtering and barycentric interpolation for vertex attributes. However, bilinear interpolation often fails to achieve enough smoothness. In this example, a camera close-up reveals the blocky appearance of the texture magnified with bilinear interpolation. Using bicubic interpolation significantly improves the texture filtering quality. High-order interpolation can also be used for 3D primitives. For embedded deformation, quadratic interpolation of tet mesh vertices avoids faceted appearance of the deformed object. For volume rendering, tricubic interpolation reduces the undulation of the smooth function reconstructed in a 3D grid. Despite the benefit in quality, high-order interpolation has not been widely used in real-time rendering applications. One reason is that it has significantly higher computational cost, and the quality improvement might not be sufficient to justify the sacrifice of performance. Another reason is the lack of hardware support. This enlarges the performance gap between the linear and high-order interpolation, while requiring developers to figure out a fast software implementation. These problems have been investigated by prior work. Some works introduce partially accelerating bicubic or tricubic interpolation on existing GPUs by specifying sampling coordinates that make GPU return partial results through bilinear or trilinear taps. However, these partial results still need to be combined manually in shader code, and they may require modification of texture to improve performance. Some other works propose FPGA implementation for high-order interpolation to improve its performance. However, these FPGA implementations require a lot of dedicated hardware resources, and they are often limited to specific tasks like 2D image magnification. These make them not very appealing to graphics card vendors. In addition, high-order interpolation on simplexes like triangle and tetrahedron has not been supported by graphics hardware. Our method addresses the existing problems of high-order interpolation. We first present a unified refactoring of quadratic and cubic interpolations as standard interpolation plus linear interpolation of high-order terms. Because of that, we can reuse the hardware linear interpolation units on existing GPU with only minor modifications to compute high-order interpolation in high performance. Our formulation supports both 2D and 3D grids and simplexes, allowing it to be used for a wide range of applications. In addition, the high-order terms can be dynamically skipped when their magnitudes are small, which can save more computation. Our method allows achieving high-order interpolation quality with a cost similar to linear interpolation in many cases. Like in this texture filtering example, we only use 1.6 times more computation than bilinear, much better than the state-of-art implementation on current GPUs. The key to our method is refactoring high-order interpolation into multiple linear interpolations. To explain our method, we begin with a simple 1D example, which is interpolating 2 points along a line using a parameter s. We use this L2 symbol to denote linear interpolation in 1D with 2 points. The right-hand side of this L2 equation can be defined as the linear interpolation operator. We will reuse this operator later. We can extend this to quadratic interpolation Q3 by adding a midpoint. This uniquely defines a curve passing through the 3 height values. By rearranging the terms, we can express the same function as the linear interpolation plus a high-order term that includes the difference between the desired center value and the linearly interpolated center value. If the difference term is small, we know that the linear interpolation provides a good approximation. For cubic interpolation, we can define derivatives at two vertices to define a unique cubic polynomial. This is also known as the Hermite form. After rearranging, we rewrite cubic interpolation as linear interpolation plus a third-order term that includes a linear interpolation of the difference between the desired derivative and the derivative of linear interpolation at the two vertices. Using a similar kind of rearranging, we can express bicubic interpolation as the combination of several bilinear interpolations. This starts with the standard bilinear interpolation using 4 points. And we add another bilinear interpolation of the 4 horizontal d terms. Just as in 1D case, there are differences between the desired derivatives and the derivative of linear interpolation along the edges. This bilinear interpolation result needs to be scaled by a 1 minus s times s factor before it is added on the previous result. Because we are in 2D, we need to consider vertical derivatives as well. This adds another scaled bilinear interpolation. Finally, we include another bilinear interpolation that interpolates d terms for second-order derivatives. And we get a complete bicubic interpolation using 16 data points. In fact, we can ignore the term that involves second-order derivatives and still get no quality reduction in practice, as we will show in later results. This is because the term we ignore is close to 0. This simplified form only uses 12 data points and is simpler to compute. In our paper, we show that other 2D and 3D quadratic and cubic interpolation can also be written as bilinear interpolation plus multiple scaled bilinear interpolations, and this allows a very efficient hardware implementation. Before I explain the details of our hardware's modifications, let's review the existing bilinear texture filter pipeline on today's GPU. This is a diagram of the texture filter unit. It reads 4 texels from the texture L1 cache. These texels are passed to the bilinear interpolation unit, which also receives interpolation weights as input. Note that to support reading unaligned 2x2 blocks in parallel, the cache is usually divided into 4 banks that store texels with interleaved indices. Bilinear interpolation unit then computes the interpolation result. The result can be optionally scaled and accumulated on top of results of previous interpolation passes for anisotropic filtering and trilinear filtering. In this example, it simply outputs the color interpolated from the 4 texels without scaling. To support high-order interpolation, we take the existing pipeline and modify the circled part. The texture L1 cache is modified to have 16 banks. This allows reading up to 4x4 blocks of unaligned texels in parallel, which is good enough for bicubic texture filtering. An additional unit is added to compute d terms, or high-order difference terms. To see how it works, here is an example of the 12-point bicubic interpolation. It starts with a bilinear interpolation, which is computed in the same way as the previous example. Then the d terms are computed. We assume cadmium spline derivatives, so a d term uses 3 data points, in a form that's relatively cheap to compute in hardware. The other 3 horizontal d terms are computed in a similar way by hardware in parallel. The 4 horizontal d terms are bilinearly interpolated. Then we use the existing accumulation and scaling units to scale the result with the factor 1 minus s times s, and add it to the result of the previous bilinear interpolation. Similarly, we compute the bilinear interpolation of the 4 vertical d terms, scale the result by 1 minus t times t, and add it to the previous sum. This completes our bicubic interpolation using 12 points. It's possible to add one more bilinear interpolation to use all 16 points to match the result of a standard bicubic interpolation. But the d terms need more operations to compute, which requires a greater error cost when modifying the existing hardware. Since bilinear interpolation is the bottleneck for computation, the number of bilinear interpolations determines the speed of the high-order interpolation. Here we list the number of bilinear operations required for each interpolator. Note that we outperform the state-of-art methods which compute the same cubic functions with partial hardware acceleration on existing GPUs. However, we can further reduce the cost by adaptively skipping d terms that are too small. This usually happens with images that have smooth gradients. If the magnitude of all d terms in a bilinear interpolation are below a user-specified threshold d min, the entire operation can be skipped. This simply means that depending on how much of the data are low frequency, the cost of high-order interpolation can be made as cheap as bilinear or trilinear interpolation, with a very similar quality as a full computation. To support fast 3D texture filtering, we increased the number of banks in the texture L1 cache to 32 in our final design. This guarantees that in tricubic interpolation, all 64 texels can be read in 2 cycles, which is in the same speed trilinear interpolation is performed. So, the tricubic interpolation can be performed as fast as trilinear interpolation if all d terms are skipped. Our formulation can easily extend to simplexes by switching to barycentric coordinates. By defining d terms on edges and faces in a similar way as in grid interpolation, we can define quadratic and cubic interpolation for simplexes of any dimension. See our paper for details. This formulation allows us to use the existing texture bilinear interpolation unit to support high-order barycentric interpolation for triangles and tetrahedra defined on a regular grid, which extends a prior work that uses texture units to do linear barycentric interpolation. More details can be found in our paper. Our paper also describes how to modify the existing hardware to support high-order interpolation on unstructured triangle meshes. For unstructured meshes, d terms usually need to be pre-computed. Our adaptive scheme allows them to be skipped using a threshold to save storage and computation. We evaluate our method in a wide range of real-time rendering applications, covering both grid and simplex interpolation. We will show some results here. The more complete results can be found in our paper. First, we are going to show some 2D and 3D examples for grid interpolation. We use bilinear operations as the performance metric. Since we compare methods on slightly different hardware, this provides an estimation of the relative scale of the actual texture filtering performance. One use case of high-order interpolation is temporal anti-aliasing. Without anti-aliasing, effects like jagged edges and aliasing of specular highlight can be distracting. By jittering the camera in every frame and accumulating subpixel samples over frames, temporal anti-aliasing can achieve the effect of supersampling without actually paying the cost. However, on the camera or object motion, blurring can happen. This is because a reprojected position in the temporal history buffer often lands at fractional pixel location, which requires interpolation to gather colors from nearby pixels. This image is captured during camera motion, so you can see the resampling blur here. Using bicubic interpolation significantly reduces the blurring. Let's scroll back and forth to compare bilinear and bicubic resampling. Our 12-point bicubic interpolation produces virtually identical result to the standard 16-point bicubic. Let's scroll back and forth again. Yeah, you can see no difference. In this In this image, we enable adaptively skipping d terms using a threshold of 0.03. This turns more than 60% of the pixels into bilinear interpolation. Since high-frequency regions are not affected, it is still hard to see difference from non-adaptive bicubic interpolation. Let's scroll back and forth again. It's still very hard to see any difference. Now we switch back to bilinear interpolation. Here's the heat map of our adaptive bicubic interpolation using the specified threshold. Our 12-point bicubic interpolation has 3 bilinear interpolations. 2 of them can be adaptively skipped. This heat map shows that bicubic interpolation are mostly preserved at high-frequency regions like object edges, which is desirable. Looking at the performance, our adaptive bicubic only uses 39% more bilinear operations than pure bilinear interpolation to achieve a result almost identical to full bicubic interpolation. Without adaptive clamping, our 12-point bicubic uses 3 times more bilinear operations than bilinear, but it is still cheaper than standard 16-point bicubic, which uses 4 bilinear operations with our method and 5 with the state-of-art method. For texture magnification filtering, our adaptive bicubic interpolation also achieves heavy reduction in bilinear operations compared to the full 16-point bicubic interpolation and 12-point bicubic interpolation, with only a small amount of error. Here we show a volume rendering example where volume density values are queried during ray marching using a trilinear volume density interpolation. Although isotropic scattering is used to give it a smooth appearance, the edges still look blocky. This blocky appearance is largely improved using our 32-point tricubic interpolation, which uses 4 times more bilinear operations than trilinear interpolation. Let's flip back and forth to see the difference. Note that our 32-point tricubic is mathematically equivalent to the state-of-art method that uses 7 hardware trilinear taps to approximate a standard tricubic, but our method requires less bilinear operations in hardware. Using adaptive tricubic interpolation makes virtually identical results, but heavily reduces the bilinear operation required. Here we compare again with trilinear interpolation. Next, we look at an application with simplex meshes. We use storage size for d terms and shader execution time as our performance metric. This is because when unstructured triangular meshes are used, as in this example, d terms need to be precomputed. These two metrics enable us to measure the performance of our method in a pure software implementation. The application we tested is precomputed radiance transfer. Common implementation precomputes spherical harmonics transfer vectors on all vertices in the triangular mesh, allowing real-time self-shadowing and self-reflection in a dynamic low-frequency lighting environment. Because of linear triangle interpolation of transfer vectors, the object can have a faceted appearance. We solve this problem by quadratic interpolation. To do that, we precompute additional transfer vectors on edge midpoints. The quadratic interpolation result is much closer to the path tracing reference. Let's flip back and forth to compare. But quadratic interpolation also takes 4 times more storage than linear interpolation, and the shader execution times is 5 times longer. Our adaptive quadratic interpolation uses a compacted storage that discards all d terms below a predefined threshold 0.015, which eliminates 75% of edge storage. The shader execution time is also reduced from 0.3 milliseconds to 0.19 milliseconds. By flipping back and forth, we see that the quality is almost identical to full quadratic interpolation. A visualization of non-empty edges shows that remaining D terms concentrate on high curvature regions. Again, this shows that our method can automatically exploit the sparseness of high-frequency signal to achieve high computational efficiency. In conclusion, we have presented hardware-adaptive high-order interpolation. By providing a unified, computationally efficient mathematical formulation for high-order interpolation, we allow general high-order interpolation to be computed efficiently on the GPU with our proposed minor hardware modification. Our method further allows adaptively skipping computation of high-order difference terms to save computation cycles. Our method dramatically improves visual quality in a variety of applications with only minor additional cost over traditional linear interpolation. Thank you for listening.